So we're at 4:01. So let's talk about our 4 o'clock presentation. This presentation is going to be given by Professor Ninghui Li. He's a professor of computer science here at Purdue University. He's been doing research in security and privacy, including data privacy, applied cryptography, access control, trust management, and human factors in security and privacy. He has published over 150 reference papers in these areas. The list of awards is too long to read now. Just suffice it to say that he has been awarded numerous times. He's chaired many councils and committees. He's got a broad exposure in this whole ecosystem of cybersecurity. Professor Li has served on program committees of over 150 international conferences and workshops in computer security, databases, and data mining. In 2014 and 2015, he has served on as the program chair for the ACM Conference on Computer and Communication Security, ACM's flagship conference in the field of security and privacy. His research has been supported by multiple NSF grants, including an NSF Career Award in 2005. His research has also been supported by Air Force Office of Scientific Research, Army Research Office, National Security Agency, IBM Research, Google, and Samsung. So with that, I will turn it over to Ninghui to start his presentation.
Thank you, Jerry. Can you hear me? So
I can hear you fine.
Okay, good. Let me thank you for the introduction. Let me start sharing my screen. Okay. All right. So yeah, thank you for coming to this talk. Today I want to talk about contact tracing. So I think most of you probably have heard the term in our fight against the COVID-19. So in particular, in this talk, I want to focus on what's known as the proximity-based contact tracing. So essentially, you use mobile phones and they will broadcast via Bluetooth and then detect other phones that are close by. So many protocols have been proposed. And the reason that I got interested in this, first, I got involved in looking at the COVID-19 in like late February, early March, when I saw a danger of the rapid exponential growth, but I hear relatively little at that time of this being discussed. So I wrote a couple of open letters. They are available from my homepage, so they are kind of dated. But after a couple of weeks, I think around mid-March, alarm is being sounded everywhere. So I stopped writing those open letters. And then later, I got a project funded through this rapid programs from NSF on dealing with COVID-19. And we are mostly looking at technology based on mobile phones. And this contact tracing is one major, this class of technology. So we studied that in quite a bit of detail over the last several months. So this was based on that research. And this is joint work with Fabrizio, Weicheng, and Tianhao, our graduate student here, and the professor Elisa Bertino. So contact tracing has been used as a major tool in fighting infectious diseases. So these they can be done without modern technology. So essentially what happens is after individual is tested positive, then the public health personnel, these are known as the contact tracers, they will contact the patient and then they will work with them to help them remember where they have been and which people they have contacted with during the time that the window that they are infectious. So this is very manual intensive action, and sometimes and it's always there's always contacts that people cannot remember, or you just don't know, right? So you talk with some, or you ride a bus, public transportation, you don't really know which are the other people nearby. So there's room for technology to help here. And one major privacy requirement in traditional contact tracing is when the contact tracer contacts the exposed persons about their potential exposure, and they shouldn't give out the identity of the patient. So that's a property that the privacy requirement in traditional contact tracing, that's what we should try to achieve when we use modern technologies. And many different technological tools have been used for contact tracing. So South Korea is one of the countries that was able to quickly stop exponential growth, turn it into exponential decay in a couple of weeks. So I think that was mostly in February and March. And I read quite a few articles on how they were able to do that. They used the many tools to do contact tracing. So in South Korea, e-payment, smartphone-based payment is widely used. So this data, the government access this data and use this to determine who was where when transaction occurs. And they also use closed-circuit TV footage. So I read in some article saying that there's one study found that if you walk on street in say Seoul, every couple of seconds you will show up in some video, some CCTV camera footage. So that data is also used to identify who are adjacent to a patient. And also some other countries use some other countries and regions use special devices. So we read that in Hong Kong there's smart bracelets are used to help enforce quarantine, so that if a person in quarantine move too far away from the location, then this will maybe beep or so to remind the individual. And other countries use smartphone location data, and there are two sources of such location data. One source is from cellular service provider, which cellular service provider can locate the phone, but not to very high precision. So maybe I think within maybe several hundred feet. So I read that Israel uses this kind of data to do contact tracing. So in this case, it's yeah. So it's not, you can't get very precise contact tracing, but at least one source I read, they said 1/3 of the new patient during some period of time were discovered through this this kind of location data. And an alternative is you can ask user to each download the phone, and then you can record the GPS location and the time, and then this data is then need to be uploaded, and then if every user upload this data, then they can be matched, and then you can detect contact. So the downside of using location data is this provides a new surveillance capability. So this was something that did not exist before, but now there is an entity here can essentially trace the location of either all users in the case of service provider or the users who use this app. So because of that, the mostly widely used contact tracing technology, or at least the people that garnered the most interest, uses proximity. So each phone will install an app which will use most of these apps use the Bluetooth low energy protocols, so that they can broadcast random beacons. And then the receiving, another phone also have the same app, can receive the signal, and based on the signal strength to determine how far this signal is from. And if it's close enough, then can record this signal, record the message that's being broadcasted. And then this information can be used together to determine whether a contact has occurred. And then a user who had contact then will be alerted. So there's also one app from CMU that uses ultrasound in addition to Bluetooth, because according to their research, ultrasound can determine distance more accurately than using Bluetooth. So because we are running a protocol here, there's a lot of possibilities. We can use crypto in here, and it's possible to achieve a better trade-off between the ability to do contact tracing and protecting the privacy of individuals. So this talk, we will focus on this proximity-based contact tracing. So another question is, why do we study contact tracing now? So even though we are in the middle of the COVID-19 pandemic. But I think at this point it's pretty clear. I guess our salvation from the situation is really going to coming from vaccines, which should come out soon and should be hopefully soon, and then hopefully will be widely deployed maybe by mid next year. I think that's what I heard from many sources. So in some sense, the contact tracing is most useful at the early phase of I guess before it become a pandemic in some sense. If we are able to contain it and then eradicate it, then we wouldn't incur such a high cost. We already passed that, and also while there's lots of effort and interest especially from security community in contact tracing. My opinion is that actually the role of contact tracing, the role it can play in fighting a infectious disease is fairly low unless there's near universal deployment. So there's a simple fact: if we have a p fraction of the population use this protocol, then we can only expect to detect about p square of the exposure. So essentially, exposure can be detected only when both users who are close together run the same app. So if we assume just a random distribution, then that's what we get. So that means that if we have 30% of population use it, then we can get about 9% of the event. So that's not really high. And in fact, not every user has a cell phone. So US cell phone penetration is slightly higher than 70%. So that means even if all of them deploy contact tracing, we can expect to capture about half of the event. So of course, we don't have to capture all of them for contact tracing to be effective. So in some sense, our goal is to gradually reduce the transmission, this transmission number. So reducing the average number of person infected by one person. If we are able to reduce that from 1.1 to 0.9, then we are going to turn exponential growth into exponential decay. So every little bit help, but still. Unless we have a very, very high penetration rate, this is not going to be the main thing that we can rely on. My belief is that without a central deployment, this proximity-based contact tracing cannot play a significant role. So that means that it's really the public healthcare authority need to be involved. And in fact, other part of the protocol, for example, testing status, authenticating test status, also need to involve that. So there really need to be a coherent strategy of a nationally deployment based on the, I guess in the case of US, the CDC should be getting involved. This having every state working out their own solution doesn't really help much, in my opinion. So even though I believe whatever thing we learn about contact tracing probably are not going to help too much on COVID-19, unless we are really, really unlucky. So then the COVID-19, either the vaccine fail or some other reason that we really need all the other things together to fight COVID-19. But even if these cannot be useful for cannot be much value for fighting COVID-19, I believe it's very important to study this technology and understand what kind of technology should be deployed to achieve the best trade-off between privacy and effectiveness, because there's going to be a next one that's similar. So over the last 20 years, we've seen three major this respiratory transmitted infectious diseases that this known as the spillover event, where the virus jump from one species to another. And I think most of these are scientists believe they originally come from bats. So in 2002, it's the SARS, the original SARS, and then in 2012 we have MERS, Middle East Respiratory Syndrome, and both of these are they are more deadly than the SARS-CoV-2, but they're harder to transmit. So and that combination result in the case of SARS, it's countries use a huge effort to basically crush the virus, eradicated it. And MERS, because it's the transmission seems to be even less than SARS, so it seems to just somehow went away after a few years. And SARS-CoV-2 have the property that it's much less deadly than the previous one, but it's still deadly enough to cause a significant damage, and it's much easier to transmit. So it's, in some sense, this is in terms of financial cost, this is a deadlier combination. So I tend to think that if COVID-19's fatality rate, if it's 10 times higher, I would think that the disease are already gone by this point, because people would treat it much more seriously, and much more effort will be applied in the early stage to crush it instead of letting it spread. On the other hand, if its fatality rate is 10 times less deadly, even though that's still more deadly than normal flu, but it probably doesn't warrant the current cost incurred by the current global effort to fight it. But because it's in this range, it's high enough to be very damaging, but not high enough so that everyone view it as a huge enemy that has to be crushed at all means in the beginning, so that there's a uniform effort. So that resulted in probably the most high-cost disease, at least in modern history. But looking at this, we can expect the next one will come. The next such a disease will come, and we should be better prepared and not repeat the mistakes we're making this time. So the hope is that if you have to figure out how proximity-based contact tracing or other technology-based contact tracing that offer right trade-off between privacy and utility, we can figure out how those technology work, and we can reach a consensus that this should be deployed. And then this should be, the technology can be kind of dormant in a sense, and then it can be activated when needed. Then we'll be better prepared the next time, because in the early phase, this kind of technology are really useful, because you really want to get all the contact and then have them isolated, and then that hopefully this will reduce the transmission number low enough that we are able to crush a disease before it become a pandemic. So that's, in some sense, the high level goal is I want to understand what kind of technique, what trade-off do they offer, and then what offer the best trade-off, at least in our opinion. But we also give the landscape so that other researchers and policymakers can try to make a decision about which protocol offer the best trade-off. So in these kind of protocols, we have three kind of parties. We have users. So these are just everyone, they download the app and then you become a user. And generally this app will broadcast, communicate with nearby phone by broadcasting and then storing information, and also assess distances. So in most of these protocols, the beacon that's being broadcasted are actually randomly generated, and then they are frequently changed. So depending on the protocol, they may change every 10 minutes, 15 minutes, 20 minutes, and so on. So the idea is that if someone just listening shouldn't be able to establish a movement trace of a user by hearing, oh, it's this beacon here, or it's the same beacon here, say an hour later, and then this same beacon in another place 90 minutes later. So then you cannot build those kind of mobile traces just by listening. So and when a user is tested and become tested positive, at that point the user become a patient, because patients need to do something that are different from users. They generally need to upload some data to the server, or at least inform the server that I am a patient, and then the users who had contact with me in the past some number of days should be notified. And we assume there's a central server to communicate with all the users. So technically, a server is not absolutely needed. So it is possible to have a completely peer-to-peer system doing this, but it will be very expensive, and in terms of communication-wise, and it also will be fairly vulnerable to various kind of malicious attacks. So given my argument that this is really only useful when deployed by central authority related with the public healthcare, so we assume that all the protocols use a server. So one thing we find is that there are actually many protocols have been proposed. If you just count the name, there are probably more than several dozens, but a lot of them are similar, or essentially at the protocol level, they are essentially the same. There may be other differences in terms of how the app does things, but still it's kind of overwhelming. So there are so many different protocols. How do we understand their trade-off? So what we did, I think in my view, our main contribution is to come up with this design space and the property that we think this protocol should have. And then we are able to analyze existing protocols more systematically and then identify what other protocol can be better. So the design space we have has 2 dimensions. So we look at 2 things. The first is what information do a patient report? So there are 3 possibilities. The first kind is report what you send. So every user keep broadcasting beacons. So when you become a patient, if you report all the beacons you have broadcasted to the server, then that belongs to the report send category. So then other users, they can store the protocol, the tokens, the beacons they heard, and then you can match this to determine whether there is a contact. So another alternative is to report what you received. So let's actually first look at a little bit concrete example here. How do I make this small? Okay, I think this is better. So let's look at probably the most widely used protocol. So this is a standard coming from Europe called the DP3T, and the protocol that's implemented by Apple and Google are essentially doing the same. So what they do is they will have patient report what beacons they broadcast. So if you become the patient, you send to the server what the beacons you broadcast, and after that, then someone need to do the matching. So that's the second dimension we look at. So whether the matching is done by the server, by the user, or by the server and the user running some interactive protocol. So in the case of user doing the matching, so what happens is user will download the uploaded beacons from all the patients from the server. So then each user can compare every beacon he or she received with the beacons that are uploaded by the patient. If he finds a match, then he knows that he had a contact for that beacon with some patient. Jumping slightly ahead of ourselves, that's also one of the major privacy weakness of a protocol in here, because this enables every user to know at which time and the contact of when you had a contact with the patient. So so then either from user's own memory or from user can potentially use some other app to keep track of where he or she is at different time, then the user will be able to recall the contacts when the contact occurs. So if the transmission is coming from a patient that the user interacted a few times in the past, then the user will see, oh, I interacted with the patient yesterday at lunch hour, or the day before yesterday at say 3 p.m. while I was walking through, while I was taking some class, let's say. So then from those couple of data points, it's oftentimes the user will be able to know, oh, that is a patient. So because that's the person that I interacted with at this time and this time. So in some sense, this violates the privacy goal of traditional contact tracing, where you only let the user know he or she had contact. You don't tell any more specific information. So of course, if the user knows that the only possible person I could get this COVID from is this one person, because all the other either are people I know who I know don't have COVID, or I basically only contact this one person in the last, say, 14 days. So in that case, the user will learn. So that is unavoidable. But a protocol should, in my view, the protocol should not reveal more information. This revealing exact contact time with the patient, we believe it's a significant weakness of a protocol in here. And another downside is this protocol has high communication costs. So any protocol that have users doing the matching means that users have to download all the data about all the patients through the user's phone and then do the matching. So they will generally have a high communication cost. So in order to fix this privacy problem, one protocol that was proposed is called Appiani, which uses a private set intersection. So instead of having the user download the data in the match, we do the matching between what beacon the user have and what beacon the server have. And then we can let the user figure out how many contacts there were. So how many contacts the user has had with patients. So that will reduce the amount of information the user learns. So the potential cost is the communication become even more expensive because they need to do these interactive protocols. So let's look at another protocol. This is in Europe. I think there are two main competing design is this DP3T and Robert. So in the Robert protocol, each patient will report the beacons it has received, or he or she has received, and then the server will do the matching. So in order for the server to do the matching, then the server must have all the broadcasts, all the beacons that are sent by every user. So in fact, I think in Robert, the server actually generates those beacons. So the server generates the beacons that every user use, and then just give this token to the users, and then the user should follow those, broadcast those beacons. So then the server can do the matching. This get rid of the user learning who is likely to be patient problem. But the problem is this enables the server to do tracing, to be able to recover the movement trace of all the users, so long as the server is doing passive surveillance. So if the server sets up listening stations in different places, and then and record what beacons that it listens, then the server knows where user is at a different time, because the server can associate all the beacons with user. So that, in my view, is the main privacy problem of the Robert protocol. So then finally, the way this report agreed works is the beacons that are sent by the users take the form of this kind of a Diffie-Hellman. I assume most of you are familiar with Diffie-Hellman protocol. So essentially, this is using Diffie-Hellman protocol for this purpose. So one user broadcast G to the A, the other user broadcast G to the B, and then they can both compute G to the AB. And then so long as they can upload information based on G to the AB, so that a matching can be fine if one of them become a patient. However, no one else, even if you heard both G to A and G to the B, you cannot compute this joint token. So this remove the problem of passive surveillance, because even if you heard all the token, you don't know, you can't link that to what are uploaded by users. So in fact, each user will upload. So in I guess one protocol is this desire protocol, where each user upload the hash value of G to the AB, but one user will upload the hash of G to AB concatenated with 1, the other will upload the hash of G to AB concatenated with 2, and depending on which of G to the A and G to B is larger. So this way, you have a 2 user, the thing they uploaded cannot be linked together. So even though they are based on the same G to the AB, you cannot tell, oh, these 2 users are together at some point in the past, even though I don't know who they are. So only when a user becomes patient, they will upload essentially G to the AB. That will enable the linking to be established. So after we had these 2 dimensions, we look at the protocol and we find that actually 2 of the cells do not exist. So no protocols use them. So, and we quickly find out that one of them is just bad. So it's just offer very bad the privacy trade-off. So for example here, if the patient report what they sent, then each user need to report what they heard to the server. So then based on which user heard, then even if the server does not do any surveillance, does not set up any listening station, the server immediately know that these 2 users were together because they heard the same beacon. So this is something that's not acceptable. So perhaps because of that, nobody proposed this protocol. But we find that this protocol at the bottom of this row, the bottom row and the leftmost column, we believe it actually offers the best trade-off. So this is our recommended protocol, if you will, from our analysis. So now let's look at the different properties we want for contact tracing protocols. So obviously we want privacy, but it turns out that privacy it's very complicated in this setting. So we consider 3 different dimensions. The first is whose privacy are we talking about? Are we talking about the leaking information about patient or leaking information about users? Because the protocol will leak a different amount of information about user depending on whether the user is a patient or not. And also what type of information. So whether it's the identity of a patient, or whether a user is exposed to some patient, therefore the user should quarantine if that is a rule. So that kind of information, or movement trace. Can the server or the malicious party infer movement trace from for different users? Or finally, interaction relationship. So there are protocols where even though the adversary cannot reconstruct movement trace, but he knows these 2 users were together here, together at this time and together at that time. So then the user learned relationship between different users. And finally, there's this adversary model. So what capability do we assume the adversary have? So we consider 4 different adversary models. One is just ordinary user. So what can ordinary user learn? And the second is server. So what can a server, based on what he sees, learn? And then we consider surveillance. So server plus passive surveillance means that the server will set up listening stations in places and then try to gain information from that. And server plus active surveillance means that the server will deploy these malicious devices everywhere, and this malicious device will also communicate like a phone. They will also send beacons, and then they receive beacons. So, for example, this kind of Diffie-Hellman style protocols, movement trace is secure when server is only doing passive surveillance. But when server is doing active surveillance, the server can construct movement trace, because when you can associate every the Diffie-Hellman token that you establish with a client, with a user to a particular location and time. So if you see that, you know that user is at that time and location. I believe it's important to separate passive surveillance with active surveillance, because active surveillance has a much higher chance of being discovered. So remember, we believe this protocol should be run by authority. So there's definitely public trust involved in the central server doing this. Now, if the central server does something malicious that can be easily discovered, then this will be a hugely deterring factor, because some people will be looking for this kind of issues. And if you easily discover, then it will be fine. And then the public trust will be lost. There will be huge consequence for whoever is involved. And active surveillance, because you need to actually pretend to be a device, it's easy for people to notice, hey, I don't see anyone else here. Why my phone is establishing connection with some other hidden device? So that could be evidence of surveillance. So in order for surveillance to be effective, you have to do a lot of them, and that will make it very easy to be discovered. So in terms of these privacy properties, after we analyzed each of them, we identified the key issues for the different category. So in terms of exposure status, so learning whether a user exposed, so it turns out that this can be both a feature and a bug. So in fact, later when we talk about utility, one objective there is the server will know how much each user is exposed. So then if there are users with very high exposure, then those the server maybe being a public health authority maybe can spend more effort on making sure that user is quarantined or tested early or whatever. So, and for patient identity, the main threat we have is it can be leaked to users via exposure time. So essentially, the analysis we just did for DB3T and Google Apple protocol, where users are likely to learn, a user knows which time the exposure occurs, so then can use that to infer who is likely to be the patient. And leaking disease data to the server is hard to avoid because in some sense you consider traditional contact tracing. That's what the servers, the central server's goal is to know who has the disease. Otherwise, you don't even start the contact tracing. So there are protocols that hide this information. No, actually, it's really hard to hide this information because at least the user must do something different if you are a patient. So then the server knows. And for movement trace, so it must be that it's not leaked to anyone who doesn't do surveillance. So the GPS location-based contact tracing, the main vulnerability is it will leak to individuals even if they don't even do surveillance. So the main difference in the different protocols that are relatively well designed is whether movement trace can be leaked to server plus passive surveillance. So defending against server plus active surveillance is very, very hard. And finally, for interaction relationship, the main thing we want to look at is for two regular users who are not patients, do the server know that they were together? So we believe that is a piece of information that have to be protected, because this is a surveillance capability that doesn't exist in traditional contact tracing at all. So after privacy, we also need to consider utility. So for utility, we consider these different aspects. One issue is this exposure aggregation, which I really don't see protocols discussed, but I think it can be, most protocols can be added this capability relatively easily. So CDC have this definition that contact is within 6 feet, 15 minutes. So this is a magical number of 15 minutes. So there has to be a magical number, whatever the case, right? But the issue is, what if the 15-minute threshold is reached in multiple shorter sessions? So if in a party, you join one circle talking with people for several minutes, and then you walk away, and then you maybe come back and then talk with the same person. So maybe we shouldn't have party at all in this era. But there may be cases that, let's say you go to work and every day you are likely to, say, ride the elevator together with someone. So each individual session is short, but they will add up. So because I don't think there is a magical number, the virus say, hey, let's wait until 15 minutes is up, then we transmit. Because it's really about the probability thing. So longer exposure time, whether they are separated or aggregated, will still cause increased risk in transmission. So this means that the protocol, whatever protocol used, should be able to aggregate these intermittent contacts. So that's one aspect. Another aspect is we want the server to be aware of the situation. So we look at two things. One is the server knows how much risk each user has accumulated. And the other is the server knows how much transmission, how much contact one patient produce. So this will help identify what's known as this super spreader. But this is also very critical in defending against some of the attacks that we talk about later. And these are the attacks. So I believe the society is highly divided over how to handle COVID-19. And anytime this kind of protocol is used, we have to be prepared for the situation that some user will try to disrupt the system. So the main threat we look at is the user of the system will try to create a lot of false alerts. So then basically destroy the public trust and confidence in the system. And it turns out that there are actually many ways to do that. So we identified these 6 different attacks. The first one we call drive-by eavesdropping is the malicious user just try to say either walk or drive quickly, and then hear as many beacons as possible. And then depending on the protocol, the goal is to cause all of those users who broadcast beacons that he heard think that they have exposure. So some of the protocol will be vulnerable if I think this report what unheard generally will be vulnerable to this kind of protocol. And because the different there are different receiver with different sensitivity. If you have a high precision receiver and in a big event, then it's easy to really capture all the beacons that broadcast by everyone, and then making everyone think they have a contact if this person later become a patient. And on the other side is we can have high power broadcasting. So broadcast beacons widely and cause the user to receive them to think they have exposure. So again, in a large gathering, and then if you broadcast, maybe everyone receive it. And if the broadcaster turn into a patient, then everyone thinks they have a contact. And the pooling is multiple malicious user colluding, and they each pretend to be all of them. So instead of just broadcast one beacon, they will broadcast one after another. They will broadcast multiple beacons. So this one phone acts like multiple apps, broadcasting all the beacons that are shared by these malicious users. And beacon sharing is, I guess, a little bit more extreme form of pooling. Is all the malicious users, they share the same beacon stream. So they all broadcast the same beacon. So if any one of them become a patient, then users in contact with any one of them will think they have a contact. And the forwarding is one malicious user forward what beacon they received to another malicious user who broadcasts them in their contact. So this will be somewhat similar to pooling, but slightly different, because in this case, the beacons being sent are not belong to malicious. They just belong to normal user, but these are being forwarded. And tunneling is they can do a two-way forwarding. So the two users broadcast, send all the beacon they heard to each other, and then they can broadcast those. So essentially connecting users who are at a different place, but making them think that they are close to each other. So also another important issue is how much the computation cost. So after we analyze this, we have a kind of a general, there's a general result. Yeah, I think this slide has the detailed analysis result. So I just want to, I guess, point out that in terms of resiliency, so this column, this sent user column, this is a Google Apple DP3T column. So the main problem is the patient privacy is very much compromised. So patient identity can be leaked. So the white is bad, black is good in here. So white circle is bad. So, and patient movement trace can be revealed if the server do passive surveillance, so which is harder to be discovered than active surveillance. And also it's fairly not resilient. So a lot of this attack will work against this. And the protocol that we believe offer the best trade-off is this one, agreed server. So it's a much more resilient, so it can defend against 3 other attacks than this one. But it does compromise and it protects patient privacy if the server are into passive surveillance. But when server does active surveillance, both user and the server and patient movement trace can be recovered. Even though I believe active surveillance plus server is unlikely adversary that's unlikely to happen. And also the exposure status is revealed. But as I said, this can be both a feature and a bug. So if you want the server to know how much risk one user has, then you need this exposure. But it does protect against patient identity leakage. So we have submitted a paper on this. So, and I think maybe in a week or so we'll make it available on the archive. If you are interested, then you can email to me or you can post on the Slack. So I think I'm short on time, so I'll skip this. Essentially, these 2 dimensions, they offer some trade-off. So if you have a server, then you have better situational awareness and you protect patient identity better. You have server does matching because user don't see the data. If you have user do the matching, then the you have a better protection against exposure because the server doesn't need to know whether a user is exposed or not. And the user's movement trace is better protected because the user doesn't upload anything. So then you really don't learn much about the user. So in some sense, server and user is trading off between the user privacy versus patient privacy and versus whether the server is aware of the situation. So this kind of recap some of the points that I made earlier. Essentially, my belief is that this is, I think this is a time that the community should come to a good understanding of what protocol, what trade-off are offered by each protocol, and which one, and hopefully agree on which one should be deployed in the future when we need this this technology. So I think that's the last slide. So I'll stop here and answer any questions.
Thank you, Ninghui. That was great. I appreciate that. You made a great conclusion for our first day of the symposium. Are there any questions on that you have? Now's a great time to ask them. You can either ask through the Slack channel, or you could post a chat with a question, or you could maybe raise your hand and we'll try to call on you and activate your mic so you could ask your question directly as well.
Stop sharing.
Yeah, I'm not seeing any questions at the moment, so the floor is open if anyone would like to ask a question at this point. I think we have one coming in here. Okay, we do have a question that's popped up in the chat. It says, great talk. You say, so given my argument that this is really only useful when deployed by central authority related with public health care, in addition to privacy and security challenges, how would we address the challenge that comes from citizens refusing government mandated behavioral changes, for example, masks?
Well, that's a very good question, but it's really outside the the thing that I'm looking at in this particular work, and also outside my general expertise. So it is a very hard question, but I don't know. Yeah.
That's clearly a social question, not something we can solve with math at this point.
Yeah, so I don't really know whether in societies like in US, whether mandatory deployment is actually feasible. Probably not. But I think it is possible that the capability can be built into the device, just like Google and Apple. They're already building at least a lower level, not the actual app, but the lower level. They can be part of the system. So when they're, I hope is that when there's a need, people can, well, at least some consensus can be reached that this should be deployed. Don't know what's actually going to happen.
Okay. Anything else? Any other questions have popped up? Okay, while we're waiting to see if another question pops in here before we go, I will tell you that Professor Lee has posted his slides on the Slack, so you can go to the Slack channel and review his slides there. If there are no other questions, I would like to thank Professor Lee for sharing his afternoon with us. This was a great and very timely discussion. And so let me give everyone sort of a preview of tomorrow morning's talks here. Put this on the full screen. So this is just a preview of the first half of the symposium. So there's an entire second half which includes more faculty technical talks, more industry talks, and of course our closing keynote panel discussion by Dr. Lorraine Kesselberg. That will be a great follow-on to this discussion because election and contact tracing and lots of issues are going to be explored in that particular talk. But in the when we kick it off at 11 a.m. tomorrow morning, we have also what I feel is going to be just an outstanding fireside chat keynote talk. Professor Spafford will be moderating this talk, and his two guests are going to be Julianne Galena, who's the Chief Information Officer for the CIA, and Chris Lovejoy, who is the Global Consulting Cybersecurity Leader for EY Consulting. Both very talented individuals in their field. What you may not know is that they are sisters. So it should be a really great conversation. They're going to discuss cybersecurity in both public and private sectors. So I think that's going to be a great way to kick off our day tomorrow. Our second panel discussion, which will follow, is on securing 5G. So we're looking forward to have that as well. So I'll remind you to use the Slack channel for conversations. Please visit the poster sessions and take a look at that. And we look forward to seeing you in the morning when we get started at 11 a.m. Eastern Time, Indiana time. So thank you very much, and we will see you all tomorrow.